In our continuation on the study of divisibility, we also have to figure out a way to handle problems where we may have a remainder. So remember at the beginning of section 4.4, we talked about how when you were first introduced to the concept of division in school, you were probably taught that 12 divided by 3 is 4 because you can separate 12 objects into 4 groups of 3 with no objects remaining. But what would you do if I asked you about 14 divided by 3? Well, then you could divide your 14 still into 4 groups of 3, but we'd have 2 leftover objects. So we usually state this as 14 equals 4 times 3 plus 2. We have a special name for this type of property. We call this the quotient-remainder property. And we have a theorem. The quotient-remainder theorem says, given any integer n and positive integer d, there exists unique integers q and r such that n equals dq plus r, with r being between 0 and d. That sounds a little complicated, but when you think about this, r is your remainder. D is your divisor, Q is your quotient. So they all stand for the letter that represents them. So n is the number that we're looking at, any integer n, and it is made up of D times Q, the divisor times the quotient, plus the remainder. So if we have no remainder, that means that D divides n evenly, right? There's no remainder left. So it has just the integer value q. So n equals D times q, which should sound strikingly familiar to the definition that we gave in 4.4. So what does this look like in action? Well, let's look at a few values. If I ask you, does 4 divide 54? We would say, well, no, not evenly. But we can state this using the quotient-remainder theorem. So we're going to determine the values of q and r, the quotient and the remainder, such that n equals dq plus r, and r is between 0 and d. So let's think about 54 and how we can break it down into multiples of 4. Well, 12 times 4 is 48, so that's pretty close, and I can get another 4 out of it by getting it up to 52, which would make it 4 times 13, and that gets me to 52. That's not enough, so I need to add another 2. So now I have 54 is made up of 4 times 13 plus 2, where 54 is my n, 4 is my divisor d, 13 is my quotient q, and 2 is my remainder r. So we would have q equal 13 and r equal 2. That r is between 0 and what our divisor was, which was 4. So remember, if you get a number that is outside of that range, then you need to up your quotient by another one, by another factor at least. Let's try one more. How about 4 dividing negative 54? Well, negative 54, well, let's see if we do 4 times negative 13 and add 2. Let's just try that. Well, that gets us to 4 times negative 13 would be negative 52 plus 2. Okay, that's not going to work. That's negative 50. Now we're off by 4. Luckily, that's our divisor, so what we do instead of 13 is we make it negative 14. Now we get negative 54 equaling a negative 56 plus 2, and that's exactly what we're looking for. So here our quotient is negative 14, our remainder is still 2, and our remainder is still between 0 and 4. How about 70 dividing 54? How many times does 70 go into 54? Well, that's kind of tricky because 70 is bigger than 54. So 70 doesn't really go into 54, so it can go in 0 times, which means that the entire 54 has to be my remainder. So here I have a quotient of 0, and I have a remainder of 54. And before you think, we can't have a remainder that big, all of our other remainders have been 2. You can, because here our divisor is 70. So 54 is definitely less than 70. But what this leads to is an interesting concept that some of you have probably already seen in your programming, and that's the idea of div and mod. So the way that we write out div and mod is very similar to our quotient-remainder theorem. So a number of computer languages have built-in functions that enable you to compute values of the quotients and the remainders from this quotient-remainder theorem. And we need to know, how do they work? Well, if we know that we're given our integer n and we're given our positive divisor d, then we know that n div d is the integer quotient obtained when n is divided by d. If we do n mod d, we get the non-negative integer remainder obtained when n is divided by d. So in other words, our n div d is equal to the quotient, and our n mod d is equal to the remainder. Kind of a nifty way to program. So symbolically, if n and d are integers and d is positive, then n div d equals q, and n mod d equals r if and only if n equals dq plus r, where q and r are integers and our remainder is still between 0 and d. Let's determine some n mod d and some n div d. So if we were to look at 4 dividing 54, remember we already said on the last page that this is 54 equals 4 times 13 plus 2. 13 is my q, 2 is my r. So what that leads to is 54 div 4 is the 13, and 54 mod 4 is the remainder, which is 2. Likewise, if we look at negative 54 equaling 4 times negative 14 plus 2, negative 14 was our q, 2 was still our r, so we get negative 54 div 4 was negative 14, and negative 54 mod 4 was still 2. And lastly, we had 70 divides 54. Well, that's where we had 54 equals 70 times 0 plus 54, where 0 is our q and 54 is our r. So we end up with 54, oops, I wrote 70. 54 div 70 is equal to 0, and 54 mod 70 equals 54. The real question comes in, what can I do with these in terms of arithmetic, say with modular numbers, modular arithmetic? Well, we have an example or two of that as well. So let's look at example 4.5.3 and see what we can do with our mods. So suppose m is an integer. If m mod 11 is 6, what is 4m mod 11? Well, let's start with m mod 11 equaling 6. Remember that 6 is now our remainder. So we know that m is equal to 11 times some quotient q plus 6. So if I want to find 4m mod 11, then I need to find 4m. So we'd say then 4m would equal 4 times 11q plus 6, which is 44, which is 44q plus 24. But now we want to find mod 11 of that. So what we need to do is figure out how much of this can I pull out in 11? Well, I can rewrite this as a 44q plus 22 plus 2 to make this 11 times 4q plus 2 and then plus 2. So what that means then, I want to come up here, is that 4m mod, whoops, making it 11, mod 11 then is what's left over, because this is my integer q, my new integer q, and this is my remainder, which is just 2. So 4m mod 11 equals 2. Because 4q plus 2 is an integer, and 2 is between 0 and 11. So let's try another one. Let's try a mod 7 equaling 4. We'll find 5a mod 7. Try this one on your own, so pause and come back. All right, so we've got a mod 7 equals 4, which based on our quotient-remainder theorem says then that we have a equaling 7q plus 4. So that makes 5a equal to 5 times 7q plus 4, which is 35q plus 20. And we want to know what 5a mod 7 is. So we need to pull out the highest multiple of 7 we can out of everything. Well, that's not hard to do on the first one, but we need to split up that 20. Well, it's almost 21, so it's not quite 21. We're not going to be able to pull out a full 21, so we're going to have to pull out a 14. And 14 plus 6 gives us 20. So now we can take a 7 out of the first two terms and be left with 5q plus 2 and add 6. We know that 5q plus 2 is an integer because integers are closed, right? And we know that 6 is between 0 and 7. So we know 5a mod 7 is this remainder, which is 6. The next question then is, can we write proofs with div and mod? And the answer is absolutely, like I would say anything else. So let's look at an example of what a proof would look like using mod and the quotient-remainder theorem. So I said in example 4.54, I want you to prove that for all integers m and n, if m mod 5 equals 2 and n mod 5 equals 1, then mn, their product, that is m times n, mod 5 is equal to 2. So we would write our statement as a universal conditional. So our statement, we would say for all m and n that are integers, if m mod 5 right? If m mod 5 equals 2 and n mod 5 equals 1, then mn mod 5 equals 2. So when we get into our proof, we can suppose everything is true before the word then. So we would say, let's let m and n be integers such that m mod 5 equals 2 and n mod 5 equals 1. From here, we can use the definition of mod, or you can say by the quotient-remainder theorem, whichever way you want to cite it. I usually say by the definition of mod. So by the definition of mod, we know if m mod 5 equals 2, then m equals 5q plus 2. And if n mod 5 equals 1, we know that n is 5r plus 1. We can't use q again. And we have to define what q and r are. So this is for some q and r that are integers. And then now we've used all of our definitions, so we move into showing that mn mod 5 must equal 2 if this is how we define m and n. So we would say by substitution, we would say that mn, right? We're not going to plug it back into mn mod 5. We're going to do mn and find the product first, and then we will find the mod of that 5 of that mn. So let's find m and n, m times n first. So we would get 5q plus 2 times 5r plus 1. And if we simplify, we get 25qr plus 5q plus 10r plus 2. And we're trying to find the mod 5. So we want to factor out a 5 out of the most terms that we can. And in fact, here, it's only going to be the first 3 terms. 2 is already less than 5, so we aren't going to be able to pull out that 2. So we can guess that that is definitely going to be our mod here, which is a good thing because that's exactly what we were supposed to show, is that it's 2. So here we'll pull out our 5, and we've got 5qr plus q plus r is left in parentheses, and then we have our plus 2. And now we want to show that that's 5 times an integer plus 2, because that's our definition of mod. So we're going to say, let's see, we haven't used p. We're going to say let p be equal to 5qr plus q plus r. Then we know that p is an integer because integers are closed under, and what did we use here? We used multiplication and addition. Oh, I realized my R got a little, there we go, I'll fix that. Are closed under multiplication and addition. Thus, when we keep going with our simplification, we have that mn is now equal to 5p plus 2 for some integer p. And we also know that 2 is between, hopefully you got this, 0 and 5. So now we have defined the mod 5 of mn, and it is indeed equal to 2. So we would say, therefore, by the definition of mod, or you can use the quotient-remainder theorem if you like, by the definition of mod, mn mod 5 equals 2. And it's done.